Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll extend our knowledge from being able to solve questions of motion in one dimension with constant acceleration to being able to solve any motion in one dimension, whether the acceleration may be constant or variable. And then we'll move on to understanding some concepts from the graphical perspective of motion in one dimension. The key concepts for being able to solve problems involving variable acceleration is very simple if you really understand the basic concepts. If you know how to derive the four equations we derived for constant acceleration, then you have to use the exact same concepts to be able to derive the motions for variable acceleration. So let's look at examples. Let's say I'm given the position as a function of time of a particle, and it's given to me to be x equals 2t cube minus 3t square minus 36t. So this gives me the position of the particle at any time t. And we saw last time, if I know the position of the particle at any time t, then I can be able to calculate anything. So let's say I am asked what is the velocity when the acceleration is 0. So this question has two parts. First we have to find out when the acceleration is 0, and then we have to find out the velocity at that point. So we know the standard rules for calculating velocity and acceleration from position. V equals dx by dt. So this will just be an exercise in calculus. We will come out to be the derivative of 2t cube will be 6t square minus 6t minus 36. We can even find the acceleration. It would be the derivative of the velocity, which can also be written as the double derivative. This is the notation for double derivative of the position, and that would be 12t minus 6. So we know now the velocity, the acceleration, and obviously the position at any point of time. So we'll be able to find out when the acceleration is 0. We know that acceleration as a function of time is 12t minus 6. So acceleration is 0 when 12t minus 6 is 0, which means t is equal to 1 by 2 seconds. So we know that at t is equal to half seconds, the acceleration is 0. But we know the velocity as a function of time as well. So we can find the velocity at t is equal to half seconds. That will be 6 into half squared minus 6 into half minus 36. And obviously you can calculate and find out, simplify, and whatever it will be. If we wanted to find out when the particle was at rest, that simply translates to when the velocity of the particle is 0. So in that case, all we would need to do is 6t square minus 6t minus 36 equals 0, or if you take 6 common, t square minus t minus 6 equals 0, or t square minus 3t plus 2t minus 6 equals 0, or t minus 3 times t plus 2 equals 0. Ignoring the negative root, we get t is equal to 3 seconds. So we also know that at t is equal to 3 seconds, the particle is at rest. We maybe could have been asked what is the position of the particle when it is at rest. So then all we would need to do is put t is equal to 3 seconds in the position of the particle. So this way we see, if we know the position as a function of time, we can calculate anything. We do not really need to know anything else. But that's not really true if we go in reverse. If we calculate position from velocity and acceleration, we need some other things which are called initial conditions. So let's look at that in a little bit more detail. Let's say I start from acceleration and I am given a is equal to 2t, which means dv by dt equals 2t, which means dv equals 2t dt. And I can integrate, which will give me v equals t square plus c. Okay, So now we know v as a function of time, but we don't really know v as a function of time because we do not know the value of c. And we can see that directly as well if we just tell you the acceleration, and we know that the acceleration is 2t. That means at t is equal to 0 the acceleration is 0, at t is equal to 1 the acceleration is 2, at t is equal to 2 the acceleration is 4, and so on. The motion would still be completely different if the particle started from rest or if the particle started from a velocity of 50 meters per second. We know that the motion would be completely different because even though the accelerations would be the same, the change in velocity would be the same, the initial velocity would be different. So it also makes sense to us from a physical perspective that if we are just given the acceleration as a function of time, we cannot really tell the velocity as a function of time. We need some initial condition, and that could be given in a variety of ways. Let's say our question consists of 3 conditions. So we were given a is equal to 2t, then we were given that the particle is at rest at t is equal to 2 seconds, and we are given that the particle starts from origin. In the previous question we were only given one thing, that was x as a function of time. In this case we are given 2 extra conditions. So using the second condition that the particle is at rest at t is equal to 2 seconds, we can see that v is 0 at t is equal to 2 seconds, which gives me c is equal to minus 4, which gives me v is equal to t square minus 4. Instead of calculating the constant of integration explicitly, we could have used definite integration and put in the limits directly as we have done before. And now given v is equal to t square minus 4, we can see that dx by dt equals t square minus 4, which means dx is equal to t square minus 4 dt. We integrate the two, so we can get x is equal to the integral of t square would be t cube by 3 minus 4t plus k. I'm using k only because we've used c already in this constant. K is another constant of integration, and we know the particle starts from origin. That means when t is equal to 0, x is equal to 0, which gives me k equals to 0. So that means x equals t cube by 3 minus 4t. Again, it does make sense to us that simply by knowing the velocity at any time, we cannot know exactly where the particle is. Let's say I know v is equal to t square minus 4. So the particle is going on a straight line with the speed of t square minus 4 seconds. The motion would still be very different, meaning the position of the particle at different times would be very different depending on whether the particle starts from this position or the particle starts from this position. We cannot really tell the position of the particle unless we know where it started from. So the velocity at every point of time is not enough to tell us the position at every point of time. So hence we were given 2 extra conditions. Notice that if we were simply given x is equal to t cube by 3 minus 4t, we would have been able to calculate the velocity and acceleration without any other initial conditions needed. But every time we integrate, we get a constant of integration, and we need an extra condition to be able to find out that constant of integration. So when the acceleration is given, we will need to be given other initial conditions as well. So this can be summarized as follows. If we know the position as a function of time, we can figure out everything there is to know about the motion of the particle. If we know the velocity as a function of time, to figure out everything there is to know about the motion of the particle, we also need an initial position. Now that does not really need to be the position at t is equal to 0 seconds, it could be the position at t is equal to 4 seconds or the position at t is equal to 7 seconds, it doesn't matter. If we know only the acceleration as a function of time, then to be able to figure out everything, we need to know the initial position as well as the initial velocity, because once we integrate the acceleration to get velocity, we'll get one constant of integration, and then once we integrate velocity to get the position, we'll get a second constant of integration. With every constant of integration, we'll need a new condition so that we can be able to calculate that constant of integration. Apart from these few formulas, there's another formula which sometimes is used. So if we see that v is equal to dx by dt, from that we can see that a is equal to dv by dt which I can write as dv by dx times dx by dt using chain rule. But since dx by dt is v, we have another equation, a is equal to v dv by dx. So this equation can be helpful when instead of being given the velocity as a function of time, we are given the velocity as a function of position. So let's say I'm given v is equal to 3x squared. One way to go about would be to write v as dx by dt, and then we would get 3x by 3x dx by 3x square is equal to dt, and we can integrate. But if we only need to find out the acceleration, we do not need to go through this process to find out the position as a function of time first. We can simply see that dv by dx is 6x, and that means v multiplied by dv by dx is 3x square times 6x, which is 18x cube, which is the acceleration. So the formulas we really need to remember are v equals dx by dt, a equals dv by dt, which also equals v dv by dx. And obviously what we did before for the case of constant acceleration, we get v equals u plus at, s is equal to ut plus half at square, and v square equals u square plus 2as. So using these steps, we can be able to calculate the quantities in problems involving variable accelerations as well, not just constant accelerations. The next step which is left is we need to be able to solve problems using graphical methods. So let's look at that. So if I were given the position as a function of time, let's say x is equal to t cube, from that I can see that velocity is equal to 3t square, and from that I can see that acceleration is equal to 6t. But if we were to plot x as a function of time, the graph would be something like this. And we know that let's generalize it first. If we have a graph of a versus b, then the slope at any point, the symbol for the slope is m, is given as dA by dB. That is the derivative of a with respect to b. Similarly, the area under the curve between any 2 points, let's call these points b1 and b2. The area under the curve between these 2 points would be integral of a dB from b1 to b2. So these two concepts, the slope and the area, generalize to differentiation and integration when we look at it in terms of the graphical perspective. So if we look at the xt graph, we know that dx by dt is equal to v. So we can say for sure that any point the slope will be equal to dx by dt, which will be 3t square. So from this we can deduce that if we have the position versus time graph, the slope at any point will give us the velocity, and we can look at a lot of things directly from this. At this particular point, the slope is 0. That means the velocity is 0, and we know that because the position is at a maxima. Remember, we can always join concepts of maxima and minima to these questions. That would be easy enough. So at these points, the slope is 0, that means the velocity is 0, that means the particle is at rest. Similarly, let's look at a more interesting graph, that would be the graph of velocity versus time. The velocity versus time graph of a particle at every point would have a slope, and that slope would give us dv by dt, which would give us acceleration. Also, we could try to calculate the area under the velocity time graph between any 2 times t1 and t2, And just like slope generalizes to differentiation, area generalizes to integration. This area would be integral of v dt. Here v is acting as a and t is acting as b in the previous slide. So integral of v dt from t1 to t2. But that is simply the displacement. From t1 to t2. Similarly, if we wanted to, we could look at the acceleration versus time graph. The area under the acceleration time graph between 2 points t1 and t2 would have the value equal to integral of a dt from t1 to t2. But a dt is dv, so this would be equal to v2 minus v1, which is the change in velocity. If the curve goes below the x-axis, then the area is considered to be negative. And the slope of the AT graph, it would give us something actually. It would give us dA by dt. But that's not really a quantity which is of general interest to us, the derivative of the acceleration. And we can apply this directly, and we know that if we take any graph of a versus b, the slope will give us the derivative of a with respect to b, and the area under the curve will give us the integral of a with respect to b. So for the s versus t graph or the x versus t graph, remember x and s both are used interchangeably. The slope will give us ds by dt, which will be v. The area under the curve would give us the integral of x with respect to time, but that's not really a quantity which has any physical significance. The v versus t graph is more interesting. The slope will give us dv by dt, which is the acceleration, and the area under the graph will give us integral of v dt, which would be the displacement. The AT graph would give us an area under the curve which would be equal to the change in velocity, and a slope which would be equal to the derivative of acceleration with respect to time, which is again not a quantity of general interest. And the general case, A versus B graph, remember we could also have displacement versus velocity graphs, or velocity versus acceleration graphs, or position versus acceleration graphs. So A versus B graph, in this case A is on the y-axis and B is on the x-axis. The slope would give us the derivative of A with respect to B, and the area would give us the integral of A with respect to B. Okay, so this completes motion in one dimension. In the next video, we'll expand our knowledge and move on to motion in a plane, that is motion in 2 dimensions. And in that video, not only will we need concepts of calculus, we will also need concepts of vectors, which we've already learned. Thank you.